Section 5.2 and 5.3 cover how to solve systems in the two last ways we will learn. 5.2 is learning how to solve systems by substitution. If you notice the word substitution, it looks like it has the word substitute at the very front. And that's precisely what we're going to be doing. We will take expressions and substitute them into another expression and be able to solve for variables. Now, you were handed this piece of paper and you cut it in half, and we're going to look first at the flow chart that says substitution at the top. So take a second and get that cut up. Now, let's say that we have the following system. It says y equals x plus 3 and x plus y equal 5. Substitution comes in handy when we have systems that look like this because we're going to be able to solve for one or both of the variables without graphing, since the second equation cannot be graphed in its current form. So we're going to ask ourselves the questions on the flowchart. Is there a variable isolated? So we look and we highlight. The y in the first equation is by itself. That's what isolated means, by itself. So highlight, circle, star, underline the y in the first equation. Then circle, star, highlight, underline the y in the second equation. Do you notice how there is one in each of them? Since it's isolated, we follow the yes page, and it says to substitute the expression or plug in the expression for the isolated variable, this x plus 3, into the other equation. So here's how we're going to do that. We will take y equals x plus 3, and we will substitute this expression into x plus y equal to 5. It said y a second ago, and now it says x plus 3, since that is what we're substituting in. Last part of step 2 says to solve for the leftover variable. If there were any number here, I would distribute it inside the parentheses, but there is not. So it's really like having x plus 3 equals 5. X plus x is 2x. And I solve by subtracting the 3 to the other side and dividing by 2. Therefore, I'd get that x is equal to 1. Now we move on the flowchart down to step 3. Step 3 says to substitute the value for the variable from step 2, this right here, into the equation with an isolated variable. Simplify to find the remaining variable. So here is the original expression that we did not substitute in. But we now know a value for x. It's 1. So I can substitute or replace that x with 1. Now that I only have one variable left, I can solve. Simply just add. 1 plus 3 is 4. Which means that I think the solution is 1, 4. That these two lines would cross each other at 1, 4. That's the point that makes both equations true. Now before I can finalize this answer down here, this coordinate, I need to check my work. So I will be plugging in these x and y values to the equations I had at the beginning to double check my work. The y was 4, the x was 1. Trying to see if 4 is equal to 1 plus 3. Well, yes, that's true. 4 is equal to 1 plus 3. Then I plug the other one in. This is going to be 1 plus 4 equal to 5. Is that a true mathematical statement? Yes, it is. If I have 2 check marks when I've plugged in my answer choices, I have the correct answer, so we know that the solution from solving from substitution is 1, 4. Take a second, glue this into the first page on your spiral, and flip it over. Pause until you're ready, and we will have 3 examples that we do. First example is the following system. X equals 3 plus y, and x plus y equals 7. So we're going to ask ourselves the questions from the flowchart. Is there a variable isolated? Yes. This expression right here will stand for x. So we're going to take that second expression, x plus y equal to 7, and we're going to substitute in that value, 3 plus y, instead of writing an x. We have substituted it in. There's nothing to distribute, so really this is like 3 plus y equal to 7, or 3 plus 2y equal to 7. One variable, one equation I can solve. Start by subtracting 3 from both sides. This is 2y equal to 4. Divide by 2. So y is equal to 2. That is 1/2 of the answer. 1/2 of the solution. We know it's a coordinate, and that's only a y value for the coordinate. To find the x value, the flowchart tells me to substitute the variable from step 2 into the equation with an isolated variable. Here's the equation with the isolated variable. It's what we substituted in. Well, we know that y is equal to 2, so I can replace that y with a 2. This is going to be y equal to 3 plus 2, or x is equal to 5. Therefore, my solution is 5, 2. That is the point of intersection between these two lines. You can check your work by plugging them into a calculator or plugging this answer choice into the equations themselves. I want you to try number 2 on your own. It's going to be y equal to negative x minus 4 and y equal to 4x minus 4. You first ask yourself, is there a variable isolated? Yes, both of them are isolated, but I can pick the first expression and plug it in for the second variable. Go ahead and try solving this system by substitution. If you're not sure if you got it right, you can check this one by graphing since they're both set equal to y. So what we would do is we would plug that first expression that we highlighted into this second expression for y. This would be negative x minus 4 equal to 4x minus 4. You see how this was y a second ago, and now I've exchanged it or substituted it for that expression that stands for y. Very easily I see that there's nothing to distribute, so this is negative x minus 4 equal to 4x minus 4. I would add x to both sides and add 4 to both sides, which gets rid of the 4 on this side and the x on that side. And surprisingly enough, the 4 over here. This would be 0 equal to 5x. Divide by 5. Divide by 5. 0 divided by 5 is still 0. So that is 1/2 of the answer. We still need to plug this into the other expression to y equals negative x minus 4. You plug it in for x. This is y equals negative 0 minus 4. There's no such thing as negative 0. So really, y is negative 4. Which means that these two lines would cross on a graph at the point 0, negative 4. If you have questions at this point, stop, raise your hand, and ask me for any clarifying questions. The last problem we're going to try today about solving by substitution is actually exactly from the DCP you guys took last week. X equals 16 minus 4y, and 3x plus 4y equal 8. This is about as hard as it can get. We notice that there is a variable isolated, which means we want to solve by substitution. So we highlight the expression that is solved for and the variable that it's solved for. This expression 16 minus 4y stands for x. So instead of writing 3x plus 4y equals 8, I can substitute that expression wherever the x is. This time there is something to distribute. I have to distribute this 3 to both pieces inside the parentheses, and when I distribute, I multiply. This would give me 48 minus 12y, which is what I get when I multiply both of those by 3. CLT, 48 minus 8y equal 8. Use inverse operations to solve this one variable equation. We would subtract 48 from both sides, which eliminates it from the left side. We would have negative 8y equal to negative 40. Divide by 8. This would be y equal to 5. Is that the whole answer? No, a solution is a coordinate point, so we still need to substitute that value for y back into this original equation. X equals 16 minus 4 times 5. Well, 4 times 5 is 20, and 16 minus 20 is negative 4. So what is the new solution to this system? These two lines would cross at a graph at negative 4, 5.